All right, let's do a problem involving forces, but we're going to do forces that are not necessarily nice, okay? So I've got a beam here, and the axis of the beam, this is the x-axis right through the center of the beam, and then the left end of the beam is the y-axis. So the left end of the beam is x equal to 0. And then there's this force acting over here. Maybe this is an accumulation of snow or something else over here. But there's a force that runs as 70x squared pounds per foot. All right, so the units on this 70x squared is pounds per foot. And that probably shouldn't be y, that should be some sort of a force. Okay, but what we've learned is that, and we haven't done a video on this specifically, I'm kind of doing it right here. What we find is that the centroid of a force distribution, and that's what we have here, we have force distributed along this beam, less weight over here, if you will, maybe it's snow, like I said, and more snow or more an accumulation of something more over here. And it goes nicely as 70x squared. So that's a spandrel. It's a quadratic spandrel, right? X to the second power. And what we know is that the centroid of a spandrel is given by 3a over 4, where a is the left to right limit of this function. Okay, it's the left to right limit. Here's the 0, here's a. So it's 3/4 of the way over to the right-hand side. So this is at 3 feet. So all of this weight, if you will, over here, all of this force can be concentrated at one point, and that one point is going to be 3 feet times 3 over 4. So that would be what? 9 feet over 4. 3 times 3 feet, because that's a. The a in this formula, when you look this up, it's going to say x bar is 3a over 4, and it's going to tell you that this distance in here is a. So a is 3 feet. And so I'm going to get 3 times 3 feet, that's 9 feet over 4. Right? So that's 2 1/4 feet. So all of the weight can be distributed right there. So I could basically erase all of this. But now I need to know what is that weight, right? How much force is that? So I have 70x squared pounds per foot, right? 70x squared pounds per foot. And so I need to find out then what that net force is going to be. And we'll come back to that in a second. Then I've got a force here at A. I'm going to put in an A sub x because it's a pin. So it's going to have x and y components. And then there's an A sub y. And then B is a roller, so B can only have an upward force. Right? And then I've got a 100-pound force over here. So when I do the sum of the forces in the x is easy because there's only a sub x. And if this system is in equilibrium, it's equal to 0, so there is no x force at a, which makes sense. Nothing's pushing it left and right, so why would a try to be stopping that? Then when I do the sum of the forces in the y, well, I'm going to have I'm going to have a sub y plus b minus 100 pounds. And then minus whatever this force is over here. So we've got to figure out what that is. All right, so I have 70x squared pounds per foot. And so if x is in feet, that's going to be feet squared. So the 70 must be pounds per cubic foot. Right, so my function, f of x, f is a function of x, and it's 70 pounds per cubic foot times x squared. Right, that's the function, but I need to know what, and actually that's let me think about that for a second. That's force per unit length. All right, so if I want to know the net force, I'm going to have to integrate this. So the net force is going to be 70 pounds per cubic foot, x squared dx. And so notice I've got length squared times length, that's length cubed, divided by feet cubed, so I'm going to get just force. I'm going to get just force. And I'm going to integrate from 0 to 3. I'm going to integrate that from 0 to 3. And so when I do all this, I'm going to get what? I'm going to get 70 pounds per cubic foot And then the integral of x squared is x cubed over 3. And I'm integrating from 0 to 3 feet. Well, now 0 is just 0, so that was easy. I'm going to get 70 pounds per cubic foot, and then 3 feet cubed, so that's 3 times 3 times 3, so that's 27 cubic feet, then divided by 3, so 9 cubic feet. And so this is going to have a total then of 630 pounds, and that's a force. And so the idea here is all 630 pounds are concentrated at that point. All 630 pounds are concentrated at that point. So basically, this was my distribution of force based on this function, but I'm going to ignore that distribution and I'm going to assume the entire force is located at, what did we say, 3, I didn't write that down, but it's it was 9 over 4, so 2.25 feet. So 2.25 feet, that's where that's located. All right, so I'm going to put 630 pounds over here and set that equal to 0. Okay, and this was all equal to 630 pounds. So there's my force equation, but you'll notice, of course, that there's 2 unknowns. A sub y is unknown and b is unknown, so I need to do a moment as well. So I'm going to do the sum of the moments. And I think I'll do the sum of the moments right here at A, because then I eliminate A sub y. And so I'm going to get 630 pounds. That's trying to, if I put a pivot point here, 630 pounds is trying to rotate it clockwise. So that's minus 630 pounds. This is at 2 feet, so this is at 2 1/4, so that's 1/4 of a foot, so 0.25 feet. And then I have B, and B I don't know, but if B were alone, it would try to rotate it counterclockwise, so plus B, and then B is at 8 feet, this is at 2 feet, so that's going to be times 6 feet. And then finally I have 100 pounds, this is at 2 feet, this is at 10 feet, the 100 pounds is pushing down, that's clockwise, so that's going to be 10 feet, 2 feet to 10 feet is 8 feet times 100 pounds. So minus 100 pounds times 8 feet. And all of that's equal to 0. The net moment is also equal to 0. So what have I got here? I've got minus 800 pound-feet. Well, I'm going to have B times 6 feet. And then these are both negative. This is negative. This is negative. 630. This is a fourth, so half of 630 is 315. And then half of 315 is 150 plus 7.5. So 157.5. And that's pound-feet. And then over here I've got 800 pound-feet. Okay, so I have 957.5 pound-feet. And I'm going to divide that by 8. So B is equal to 957.5 pound-feet divided by the 6 feet that you see over here. So notice the feet go away and I just get pounds, which is good because this is a force. It should be measured in pounds. Okay? And so, well, again, if I do that, 6 goes into 9 one time, leaves me with 3. 6 goes into 35 5 times. Leaves me with 5. 6 goes into 57 8 times. No. 9 times. That's 54, so that leaves me 3. And then, looks like I'm going to have some repetition in here. So that's 5 times, and then 50, which is 8 times, and then 6 is going to repeat. All right, so that's pounds. So 159, let's call it 160 pounds. And then, so that means AY This is 160. This is 730. So AY equals 730 pounds minus 160 pounds. All right, now bring the B over here. Those two become positive, 730, and the B becomes negative 160. And so I get 6,570. 730, yep, 570 pounds. A little round off in there, but there we go. All right, but the idea here is that wherever the centroid of the distribution of force is, put all of the force at that location. But you have to take that force, which is going to be a function, it's actually force per unit length, which is a function of x, and you have to integrate it in order to find out what that next net force is. All right, cool problem. Just like what we've done before, but I'm taking advantage of centroids in order to figure out where the force is located, and then I have to do integrals to find out what that net force is. Of course, if it's a nice constant, then you don't have to do an integral, but in this case, it was a function. All right, if you have any questions on this example, please leave them in the comments below. Thank you.